Hello everyone, let's continue with our experiments. In the last video, we started an experiment where your PMOS size was equal to NMOS and we did this spice simulation. The rise and fall delay came up to 148 picosecond and 71 picoseconds respectively, and the switching threshold was about 0.99 volts. The next experiment is to use a PMOS which is double the size of NMOS. Basically, the width of the PMOS will be double the size of NMOS. The length remains the same, and see what do we get. Okay, so the way to do is pretty simple. We'll open the spice deck for the DC transfer characteristics. So this is the DC transfer characteristics spice deck, and this is the width of the PMOS. If you see the one which is highlighted, that's the width of your PMOS. We just need to double the size, double the width of this PMOS than the NMOS. So let's do that. So we have 0.375, 0.375 into 2, that comes to about 0.75. Let's modify the spice deck to have 0.75. okay, and then we will and the same thing we have to do for the other one as well. The PMOS, we will make it to 0.75 for the transient analysis also, and then we need to do a spice simulation for both of them. So let's do that. We will open the spice deck. Okay, this is the area where we have stored all the files, so let's go to that area first. Okay, let's copy this one. Now we have to source the spice deck for the DC transfer characteristics, and this is the one. So we will source the file. The regular way to perform a spice simulations, we will do that. We will run it. We will set plot and see what the plots are available. So we have the DC1 over here, so because we have started a fresh simulator, so that's the plot that is available to us. Okay, display, let's see what are the plots available, and we will plot out versus in. Okay, and this is what you get. So over here, if you see the spice characteristics or the DC transfer characteristics of your CMOS inverter has shifted to the right side compared to the previous one. If we compare the previous one with this one, which we will be doing eventually, so the curve has shifted to the right side, and the reason for that is your PMOS is now a bit stronger than NMOS. It's not equal to NMOS. Your PMOS has got a width which is more than NMOS, and as a result of that, you have more area for you have more area in the PMOS for your capacitor, the load capacitor, to get charged. Okay, so it gets charged very fast. So this is the impact of that. You will see the way to compare this one with the previous curve is to identify the switching threshold. Okay, so we'll do that in a moment. Let's finish off the transient analysis for now. So we will minimize this one, and we will use the spice deck for transient analysis. So we will source the spice deck for transient analysis. Okay, we will run it. We will set plot and see what are the plots available. So in this case, this is a second simulation and it's a transient analysis, so this is called tran2. Okay, the plots that are available to us are okay. So we'll plot out versus time and the input waveform. Yes, so this is what we get. Now we need to calculate the rise delay and the fall delay, and as we discussed in the last video, we just need to go to the center point of or basically 1.25 or 50% of the full scale voltage, and then calculate the delay whenever your input crosses 50% to the output crosses 50%. So let's start with the rise delay. So we'll zoom into this area. Let's zoom into this area even more. Okay, and then over here, okay, this is even more. Yeah, and to be precise, we just need to click on 1.25. this is 1.25, and you get it as 1.014. that is one of the plots, and the other one is this one, so 1.094, and the rise delay will be 1.09496 minus 1.01496, so that comes to about 80 picoseconds or 0.08 nanosecond. Okay, so that was the rise delay, and we'll do the similar thing for fall delay as well. Let's do the similar thing for fall delay, and there we need to do a we did not do our spice simulation again, we can use the same one. So let's go to 1.25. Let's zoom in that area. We will zoom in even more towards the 1.25. Okay, and this is where you see the 1.25. Okay, let's do it, let's zoom in even more, and this is where you see the 1.25. Let's click on this one. So this point is 2.0487, and this point, this is 2.0812. So those both the points has been taken at 1.25. Let's evaluate the fall delay. So you have 2.08122 minus 2.00487. That comes to, so your fall delay is about 76 picoseconds or 0.076 picosecond. Okay, that was about the rise in the fall delay. Let's come back to the slides, and we will plot everything over here. So we saw the rise delay to be about 80 picosecond and the fall delay to be about 76 picosecond. That's right. The fall delay is 76 picosecond. And to evaluate the switching threshold of this particular curve, we'll just zoom into this area and see what do we get. So if you zoom into this area, this is the point at which your DC transfer characteristics and the line that we have drawn intersects. Okay, now to identify what point is that, we just need to draw one more line from this point to this point, and this comes to roughly about 1.2 volts. If it had been 1.25 volts, it would have been exactly at the center, but this is somewhere over here, so it's basically 1.2 volts. Okay, so the switching threshold has been moved to 1.2 volts. It was 0.99 volts for this case. In this case, it is 1.2 volts, and the reason is pretty easy to understand, because we increased the size of your PMOS. Okay, so the area available for your PMOS to charge the load capacitor, that has been increased. And as a result of that, whenever your input switches from logic 1 to logic 0, you see there is more amount of room available for your PMOS to charge and discharge your capacitor. So that's basically, you can just figure that reason out. Next is to do the spice simulation for another set of circuit. It is, you increase your PMOS width to thrice the NMOS, and we follow the same structure, we follow the same way we did for the previous case, and we get these values. I've already evaluated that. So you get the values to be, your rise delay will be 57 picosecond. Okay, and your fall delay is 80 picosecond, and the switching threshold lies exactly at the center or somewhere near the center if we don't miss off the decimal points. So it lies somewhere at the center, so we have kept the switching threshold as 1.25 volts. Okay, just for illustration. So these are the real spice curves, and the rise and the fall delay has been evaluated in the way we did in the past, in like couple of minutes back. So this is how do you get the rise in the fall delay. Next, we do the same experiment for your WP equal to 4 times that of NMOS of NMOS width, and this is what you get. The rise delay comes to about 45 picosecond, and the fall delay comes to about 84 picosecond, and your switching threshold shifts towards the right. It is about 1.35 volts. Okay, so as and when you increase the width of your PMOS, you see the switching threshold moving towards the right. I will conclude, we'll draw some conclusions out of it in maybe the next video, but let me try to draft some values over here first, and then we can do a very good conclusion on this one. And finally, you have a PMOS which has to be kept 5 times than that of NMOS, and in that case the rise and the fall delay comes to about 37 picosecond, and fall delay comes to about 88 picosecond, and the switching threshold is equal to 1.4 volts. Okay, so quick thing that you have noticed before I complete this video, the one thing you have noticed is the rise delay has been significantly reduced. When we started, it was about 148 picosecond, and now it's 37 picosecond. So rise delay basically says that the time it needs for your output capacitor to charge completely, and every time when you increase the size of your PMOS, the time required for your output capacitor to charge decreases significantly. And the reason is pretty simple, because you have a bigger area, and we are going to exactly conclude on this point, and we'll conclude about the inverter robustness behavior. So what we'll do is, let's try to tabulate everything what we got over here. So we got your WP by LP in this fashion, the WN by LN and this one, and every time your width of the PMOS is being increased by an integer of your NMOS, Okay, next you have the rise delay for all possible combinations, you have fall delay for all possible combinations, and then you have the switching threshold for all of them. So this is the table. We'll stop at this table and we will start concluding. What do we deduce? We deduce some conclusions out of this particular table, and those are very interesting conclusions. So let's try to deduce some conclusions and finish the concept of switching threshold in the next video. Thank you.